Welcome to 9.5. We are going to be looking at the dot product. Some of our objectives are to find the dot product of two vectors, find the angle between two vectors, determine whether two vectors are parallel, determine whether two vectors are orthogonal. Orthogonal is a special word we're going to use for perpendicular. So if one vector is perpendicular to the other, they call it orthogonal. Decompose a vector into two orthogonal vectors, and then compute something called work. So what is the amount of work being done on something? Okay, let's jump right in. Use the vectors v equals 4i plus 8j and w equals negative 8i plus 4j to answer the following questions. First, find the dot product v dot w. So v dot w, we will take 4 times negative 8, those are our I components multiplied together, plus 8 times 4, which is our j components multiplied together. This gives us negative 32 plus 32, which amounts to 0. And that's it. That's all finding the dot product is. The algebraic part of a dot product. Find the angle between v and w. Well, if we find the angle, we are going to be using our formula cosine theta equals u dot v over magnitude of u times the magnitude of v. This would give us our angle we would be able to solve for that theta. So let's find some things. First of all, let's find our magnitude. Actually, let's change our u's and v's to match our formula real quick. V and w are what we're working with, just so that way you don't get confused. So let's find the magnitude of v. Our magnitude of v is 4 squared plus 8 squared, which is the square root of 80, which we could reduce into 4 root 5. Let's find our magnitude of w, which is negative 8 squared plus 4 squared. This gives us 4 root 5 as well. Now let's plug everything in. We have v dot w is 0 over 4 root 5 times 4 root 5, and 0 over anything gives us 0. So this tells us cosine of theta equals 0. Where does cosine theta equal 0? That's at theta is 90 degrees. So the angle between v and u is 90 degrees. So if this is v, and this is u, the angle between them is 90 degrees. And we've talked about being orthogonal. When our dot product comes out to be 0, that tells us immediately that our vectors are orthogonal. The degrees between, the angle between them is 90 degrees. Determine whether the vectors are parallel, orthogonal, or neither. They are orthogonal. And the dot product is a quick and easy way to check if our vectors are orthogonal or not. Example 2, determine b so that the vectors v and w are orthogonal. V is 3i plus j, and w is I plus bj. So we're looking for that missing b, and we want to make them orthogonal. So in order to be orthogonal, like we just said, v dot w must equal 0. Our dot product must equal 0. And our dot product is going to be 3 times 1, which is our I components, plus 1 times b, which is our j components. So we have 3 plus b must equal 0. If we subtract 3, b equals -3. And that should make these two orthogonal. Example number 3. Use the vectors v and w to decompose v into two vectors, vi and v1 and v2, where v1 is parallel to w and v2 is orthogonal to w. So we have these two vectors. V is -7i plus 9j. So we have a vector that looks something like this. Oh, maybe it looks -7i. Anyway, we have two vectors and we want the vectors. So if this is our v and this is our w, w is 5i plus 2j, we want to rewrite v as one vector moving in the direction of w and one moving orthogonal to w. And to get us to the same place as v. So we would start where v starts and end where v ends, but rewritten as two vectors, one being in the same direction, parallel to w, and one being orthogonal to w. This is our goal. Okay, so we've been given plenty of formulas to help us do this, where we can decompose into a parallel and an orthogonal. So let's start with v1, and that's broken into v dot w over the magnitude of w squared times the w. So let's find all of our pieces. V dot w, what is v dot w? Well, if we multiply our i's, we get -7 times 5 plus 9 times 2. This gives us a -35 plus 18, which is -17. And let's find our magnitude of w. This is 5 squared plus 2 squared, which is 25 plus 4, and that would be root 29. And let's plug these in. So v dot w is -17. Magnitude of w squared just gives us 29 because it was root 29, but we're squaring it. And w is 5i plus 2j. So if we multiply this out, -17 over 29 times 5 gives us -85 over 29. That's in our I. And then -17 times 2 is -34 over 29j. So that's our vector 1. That's v1. That is our vector parallel to w. Now, v2, we take our v and we just subtract off what v1 was. And that will give us what is orthogonal to w. So v was -7i plus 9j. And we're going to subtract off v1, which is -85 over 29i minus 34 over 29j. So if we subtract the i's, -7 plus 85 over 29 we will get negative 203 over 29 I, and this is plus 85 over 29 I. Basically what I did here is turn the negative 7 into a fraction, so that way it's easier to combine like terms. 9 we would change into 261 over 29 for j, plus 34 over 29j. And now we can easily combine them because we have a common denominator. So we have negative 118 over 29I plus 295 over 29j. And this is our V2. So these are the two vectors. If we broke V into two vectors, V1 and V2, where one's parallel and one's orthogonal to W, this is what it would be. For our final example, we're going to calculate work. Find the work, foot-pounds, done by a force of 2 pounds acting in the direction of 45 degrees above the horizontal while moving an object 4 feet from 0, 0 to 4, 0. So let's get a visual what's happening here. We have 0, 0 is our starting position, and we want to move over here to 4, 0. So it's almost like we're pulling something maybe. We have a 45 degrees. So we have a 45-degree angle, and the force acting on it, this is F. So our force was, our magnitude of that F is 2 pounds. So 2 pounds of force pulling in this 45-degree angle, and we have this vector represented by 2, which is our magnitude, cosine 45, and then this vector here, which is represented by 2 sine 45. So this is basically what's happening here. You can think of something starting at 0, 0. If we tied a string to it and we pulled it at a 45-degree angle, and we want to move it from 0, 0 to 4, 0, and we're just dragging it across the floor. We want to know, what is the work done? So we want to know if this is A and this is B, we want to find our force going from A to B, so our work, sorry. So A, B, if we went from A and we stopped at B, that vector would be represented by 4I. We only moved 4 in our I direction. Our F, this vector F that we've drawn at our 45-degree angle, is represented by 2 cosine 45 I plus sine 45 j. That's our F vector. And what is cosine of 45 and sine of 45? We've talked about that in an earlier example. That's going to be root 2 over 2I plus root 2 over 2j. And if we distribute that 2 out, this just gives us root 2I plus root 2j. Or if you want to, you can factor out the root 2 and have I plus j. Now, we found all of our pieces. Now we can write out what our work is. Our work is F, our vector F, times our vector AB. So the work being done is the force times our vector, the direction. So we have F, which is root 2 times I plus j. And we're multiplying this times AB, which is 4i. And root 2 times 4 gives us about 5.657 foot-pounds of work. And we've done it. We found the work being done. The example in the text is actually really nice, and they put a nice visual of the wagon being pulled. So if you'd like another example, I would definitely suggest reading that if you haven't already. Of course, for this whole course, it is expected that you're reading the text and completing your guided notes before you watch these lectures. So if you need to go back and do your guided notes and rewatch this lecture so that it makes sense, I highly suggest doing it.